one is quite interdisciplinary. There is a bit of mathematics technicality in the second part. The one afternoon, there's lots of math. Hopefully you still enjoy. But this one, it should be more approachable to everybody. And I don't know if there are biologists in the audience, but yeah, so hopefully there are. So, okay, so the first to start, at the start, I would like to thank the collaborator over the years. This is, well, actually I stopped working on this, but it's been going on for 7-8 years. And so the one in red are all the biologists involved, which means they're also the one that collect the data, okay? So these in the middle, so these are collaborator academics. You know, Nitin Kenkre is my former PhD advisor, Simon Levine, a former postdoc advisor. And these are more my PhD students in Bristol, where we really started working on it. So all of them. Okay, so what I'm going to tell you, why I decided to work on it. So there is a little bit of biology versus personal introduction, what was happening at the time when I got interested or started to get interested. Then I'll tell you about the model. You'll see why that name. It's about territoriality. And so for those that don't know what random walk model, I think it's simple enough as I explain it, why. Now, I won't have some time to go too much in detail about why territorial formation is a stig-merge process. I'll tell you what stig-merge is in biology, but you can ask me later if you want. But what I spent time in studying this as a phase transition, you will see why it's relevant. What you see as you change the parameters of the model. And so that's the second part. Towards the second part, or a bit more than the second part, I'll tell you some analytical approximation, what you can do once you have a very complex model. No? So there's always a possibility of approximating. And then I'll mention something where eventually, I always get to the data eventually because I'm the one that motivate me from the start. So, and you'll see, I'll make some comments about that. So this is the outline, okay? Okay, so why did I decide to start working on it? So I think it was back in 2002. I was, again, this is Nitin Kenkre, my PhD advisor. I was doing my PhD on something different than biological processes. But at the time, there was a collaborator from Argentina who came to visit Nitin Kenkre, and they got involved in studying what happened just a few years before, in 1998, 99, at the Four Corner region in US, at the corner between Colorado, Utah, New Mexico, and Arizona. Suddenly there was an explosion of infection of antivirus, which in the population of mice, and eventually some humans died. So there was a lot of interest in what was going on, and so on. Actually there are many antivirus in the world, so that was specific to New Mexico. So they got involved, and and this fellow here is quite innocent and cute, but it's pretty deadly, if you get antivirus. So, well, among animals, so the passing in infection to the human is limited, but so they got involved. So my role at that time, so that I started getting involved, not specifically on modeling the antivirus, but looking at how this animal move. Because, to pass infection, you sort of have to first move, get close to another animal, and then pass it on. So some of the questions we were asking is that how do they actually move? What are the parameters which you can characterize the movement? So that's when at the time, or a few years later, I started to get involved. And the sort of way they move these rats, well, actually these mice, is that, and you go about measuring, so they actually live in this sort of confined space, they're different sizes more or less, each one, or maybe it could be one or it could be a family unit. And then typically you go in and measure you go in an area, you put some traps like this that represent these red lines, you capture them, and then you go, a few days later to see, well, actually the next day to see who you have captured, they tag the animals and then they recover where they go, 3 weeks later and so on. So they can determine essentially how they move. Now, how do you do it? So when you do that, you collect the data, and what you plot here, again, so this is over 3 sessions because they are every month they go for 3 days to do this marker capture experiment. And what you see over these 90 days, so what you plot here is the variance of the occupation probability. Right? So occupation probability means, given a location, probability that you're there. So you put all the data together, you assume the animals pretty much the same, statistically speaking, and then you look at the variance, so the fluctuations around your mean position. Yeah? And so what you see, if you are in a confined space, whichever you pick, then that value saturates. So you can't go beyond a certain size. Huh? So that was, and so what are the two parameters to characterize this curve? There are two. There is a slope, and there is a saturation value, correct? That's it. Huh? So this is, that was the data on, actually those original data, there were actually some experiment in Panama on a different mice, but that's what you do when you do this market capture experiment on animals that live in some home range. So those sort of semicircles, that you can call it home ranges or territory, as we see later. No? Okay, so that was and I got involved in this sort of analysis of it because you have to study, and I'm not going to tell you how, but then I got involved. So years before, in terms of scent marking, since the title of the talk is about scent marking animals, so there were studies back in '93, this Lewis and Murray. This is about wolves that live in different packs. These are the different packs. And they were interesting why the deer survive. There are lots of wolves. And actually, what happened is that since the packs of wolves, they stay separate, they exclude one another. So deer manage to go through in the tiny corridor in between. Well, some get killed, but so. And I mentioned this because, okay, it's another example of a mammal, which is scent marking like these other mice I mentioned to you. But so that set up a sort of modeling approach, because that's they did it in that context, which was an approach which we didn't follow. So you couple PDEs, which represent, so each PDE represents one pack, so all together. And you couple, and then since they are all sort of confined in that space, so you put a sort of a centroid, and then you put an harmonic potential or some other potential that keeps you trapped in it. And then you couple that with where they go, they leave a scent, they leave a field, and so on. And so it's a reaction diffusion kind of model. So those that are familiar with. Again, so the modeling is done where the movement is biased away from where the scent of the other pack. So that's a sort of and then you always try to go back to the center of that potential. Yeah. So that was the general formalism, or believed to be the proper one. Now I showed you. So in this case, if you plot the mean square displacement for each of these pack, then it saturates, as I told you before. But that was a surprise back then when I started looking at the data of other animals. So this is, I just found this nice movie. So this is called kangaroo rat, because as you can see, it jumps like a kangaroo, So luckily they're in that situation. So if you plot the MSD in that case, that was a surprise, Okay, the time scale is longer, So we are talking about 400 days, but it's not saturating. What's going on? So, okay, either the box that you're thinking is moving, and therefore that thing is happening, or they leak out. But clearly, if you try to model this with the sort of model that I told you just before from the 90s, it's not going to work. I mean, you're not representing that. And so that's what inspired me to sort of look at different way of modeling that process. And this is a sort of introduction. I told you that, why I got involved. So this is the opportunities to actually think in a different way. So, okay, so that's the memorization. Let me just go in and try to set up what the biological approach to territoriality is. Let me define what territoriality is. So really, what is territorial behavior? Yeah. So, well, it's pretty much is an interaction between, well, you say conspecific, so animal of the same species means, so that they exclude one another from some region of space. So you create segregation, so in space. And now, the interesting question, what are the interaction mechanisms that lead to that spatial segregation? So, well, there are different ones, and this is a pick example from the animal kingdom. And the one I'm going to tell you mostly, actually only, it's about the olfactory cues. So this is that's a fox. So, and so the difference between those mechanisms is that this is what you might call direct interaction. You hear something, you see something, then you respond immediately. The olfactory ones, which are the one we'll focus on, this is like a radio station, it's a broadcast. So an animal just stop by somewhere, leave a scent, and whoever later on goes there within a certain amount of time, you are outside in the environment, after a few days it's gone, then you pick it up. So that's why it's a broadcast, and it's sort of a delayed interaction, if you want, no? So only later on, they get picked up. And so the name for this is called indirect interaction, to compare to the one above. So how do you model this process? If you forget about PDE that I was telling you about, but just in general, the mechanism. How do you model that mechanism? So again, this was the one that they decided to model, creating this field, this reaction diffusion. But there is another way of thinking, where you actually go after the actual mechanism, the event of interaction between two animals. Yeah? So you don't create a field of animals and a field of scent. You're just going after the individuals. Huh? So, and then you actually have to worry about the stochasticity of that event. Huh? So remember, the PDE are representation of overall stochastic process, but this you really go after the stochasticity of the event. So if you want, the first approach that I mentioned is you sort of think about creating an effective potential of interaction. And the territories they form, as I told you, you put some dense site and everything sort of move around, and then it's always come back towards the center. So you have a relaxation mechanism that you're looking at. So this other one is a completely different approach, and it's actually, I was inspired by, if you look at some of the literature by Denneborg in particular, long ago, so in the 90s, he modeled these autocatalytic models of ant behavior. And so what that is, so the territories come up as an interaction between lots of elements, and it's called emergent process. No? It's a classical complex system studies. No? So I was inspired by those models, and to come up with a model for our foxes. No? So, okay, so what is exactly scent marking and how that territorial behavior occur in that context? So there are a few elements necessary. So you need an animal to scent, to deposit some scent, which stays there. Yeah. So for some time, not forever. Yeah. Again, you are in the environment. Those particles they evaporate, or they get, they are not sensed anymore. Then, if you want to defend that area of space, you want to claim that it's yours, you have to always go back, no? So you need to renew that scent. So you need to go back there at the specific location, wherever. Yeah. Then, now the other animals, once they encounter the foreign scent, not your own, then you have to retreat. Typically they do it because otherwise they go in, costly fight, and you don't want to get in those fights. So that's what typically happens. And so, as I told you, it's an indirect interaction. And so this you might call indirect because it's a scent mediated, it's mediated by a scent interaction. Yeah? So these are the ingredients of this territorial, and so you can call it territorial defense, and for which you avoid conspecifics. So how you model this? Well, you don't model, remember, every model is wrong. So, but I have to tell you what have we modeled. What is specific that we have modeled is that we try to follow what I mentioned, those elements. So you think about agents. Let me use the word agents. Yeah, the biologists like that word agents. So and they move. Okay, in this case we use a lattice to make it simple computationally. So you discretize the space. You have a lattice, and you have these agents that move randomly in space, and they interact because wherever they go, they leave a scent. And the others, there are lots of agents there, and the others, when they encounter the foreign scent, they retreat. So we try to follow exactly what the interaction mechanism is. So in other words, you heard me saying random walk, so that's why you probably now understand why the territorial random walk models. So when you move randomly on a lattice, you have the so-called agents, are the so-called random walkers. Yeah, so I'll explain you a little bit more in a second. So again, you have to choose how they deposit scents. Do they deposit scent all the time, or only when they are near the boundaries? There are different strategies there, not for the animals. So in this context, the fox that we are looking at, they do it all over the space. They do all the time. and they're called hinterland markers, biologically speaking. That's what they call it. And so wherever you go, you deposit a scent. Then, so when you encounter a foreign scent, animals retreat with some probability. Yeah, I mean, it's not certain that you retreat, but there's some probability for you to retreat. And so you have some sort of partial exclusion. If you retreat with certainty, you have full exclusion. You know, this is partial exclusion if you want, in general. So I'll treat only the full exclusion case for you. And then the scent decays. There is a time scale, which is fundamental, for which the scent disappears. So it means it's, I mean, that area is not claimed by anybody, no? It's free to be taken over. And now, specifically, you know, this is for the biologists. Food for our foxes is not a limiting resource in the city of Bristol, because we analyze the data on the city of Bristol. It's like plenty of food, you know, more than what they need. So in this case, cost doesn't, you know, affect movement. And in the specific time scale we look at, so there is no animal reproduction. No? So this is the sort of model we looked at. So we simplify a lot because the real biology often come in here. No? So this is how we build the model. And so now, as I said, there is some probability for you to respond to the scent present or not, and how it decays. So these are two ingredients that you have to decide what you look at. And in fact, I want to give you a picture here. So suppose you encounter a scent which was deposited tau time ago, yeah, since tau time ago. And so what's the probability? You have to put a function there, no? So you have to choose a function. So this is your time over an overall time, you know, active scent time, let's say, which when it becomes exactly t, then there is no scent. So the scent has decay, no? 0. But the way it decays, you can pick, no? As you can see, obviously. So the probability. Now, so depending how you pick the decays, if it's soft or not, then you can have, okay, this comes from a simulation eventually, but you can have, as you look at the occupation probability of two neighboring animals, you have lots of overlap, you know, and you look at this one, this overlap is minimized. So if you make really a step function, then the overlap is only at the boundaries. Huh? And so this is just to simplify the analysis. That's what we started with. So that's what the model that I'm going to tell you about has. Huh? So every animal's encounter a scent, you keep track of the timing of that scent when it was deposited, and if an animal encounters a scent within that time scale, then it's going to retreat. If not, then that territory is, I mean, there is no scent, no? So then you're free to go. So now specifically, just you have to imagine it's a computer model, so it's a simulation model. So what do you actually do? It's actually, relatively speaking, simple. So there is only a presence-absence. At the site, you have to know if there is a scent of a foreign individual. So imagine this is a lattice, yeah? So yeah, I just pick up an example of two animals, which are these, you know, field dots. One is red and one is blue. And the open circles is where this red animal has been in the last active scent time steps. Huh? So because it's still active. So this is the example. In the next time step, this fellow, it's a random walker in nearest neighbor, it can move in 4 directions, equally likely. So it's just diffusing. And this one instead, because it has encountered the scent of the other animal, has to retreat. You see? So the next arrow, it's away from where, you know. So that's the interaction. So the interaction is exactly this. Yeah. So in other words, so this is, it's as simple as this is, to build this model is very simple. Eh? So maybe just have to follow the rule. So, and the other beauty of this model is that there are only 3 parameters. Fundamentally, there are 3 parameters. Well, the density or the number of individuals will matter. Then the movement of the animals will matter. Are they just diffused? This is example view. Are they just diffusing? Are they correlated? You know, you can have different statistics. And the other key parameter, as I told you, the active scent time. You know? So if you can imagine, if you have a very long scent time, so those territories are very static, no? If you're very short, everything moves like crazy, no? Yeah, so in fact, if I show you some of the simulation, individual simulation case, so this is a snapshot. All the colors are different scent, which has been deposited within an active scent time, TA. And when you see white, it means within TAA time steps, no animals has deposited anything. Is that clear? So in other words, I'm not showing the animal here, I'm just showing the scent, but if there is an animal here, then the next time steps, if it goes here, then it becomes of that color because it takes ownership of that territory. So in fact, depending on the value of TA, the active scent time, as I told you, if it's short, then it's like you'll see crazy movement. If it's long, it's sort of more biological relevant. So this is, it's a relative short time scale, relatively speaking. So I think this is a movie. Yeah. No, sorry, this is actually, so this is a bit fast for a real biological system. So if you pick a color, it goes all over very quickly. Okay, there are periodic boundary conditions here, just to make it simple. But and you see lots of white spots because they don't last that long. Those, but if you pick just twice as big, the active scent time. So this is a more relevant biological scenario where you see each eventually, as it thermalizes, each territory has 6 neighbors. Then as you tessellate the terrain, you expect to be 6. No? So this is a more. So this is again. I'm not showing the animal. So if you want to show the animal, after do your simulation, of course you can track it, and then what you typically do is that you plot where the animal have been integrated over time. So this the biologists call it utilization distribution, and in this context, or the cross is where you start tracking from the simulation, and then you can see it's highly heterogeneous. They all move in the same way, but just the randomness generate all this heterogeneity. Yeah. So in fact, you use the term heterogeneity is endogenous generated. So the terrain is uniform initially. Yeah. So this all the interaction is what generates this heterogeneity. Okay. So this is the model. That's what the model gives. Yeah? So now, as the title has stig merging, I realize it's too long if I start telling you a lot about it. But let me just connect it at least. So what is stig merging? So this actually it's a word that Pierre-Paul Grasset in 1959 coined, looking at termites. They were building a nest. Okay. So and in constructing nest, these animals, what they do, they go in a location. I mean, typically they choose something and then they spit it out. But in doing that, you leave sort of a signal for the others to come in. So there is a feedback mechanism. And so eventually everybody starts planning. But, there are lots of mounts they can build, and then eventually one wins. No? And so how is it? Because just the randomness of the number of individuals that go and hit that the one where happens to be there, then they start creating this. No. So in other words, if you think conceptually, for the context of the territoriality that I was telling you about, you have always a stimulus and a response. There is a feedback loop. So in the context of animal depositing scent, so SI is the stimulus, which is the scent deposited by animal I. There are lots of animals. Yeah. So, and then that creates a response on the animal J, because when they encounter, for instance, retreat. At the same time, that animal then sense again, and so on. So there is a sort of feedback loop that is present, and there are salient characteristics. If you read this nice brief history of stig merging by Teola and Bonabo, there are salient characteristics of how to define stig merging interactions. And well, okay, again, ask me later. So we wrote a paper where actually we show that that's the case. So territoriality is a stig merging interaction process. So let me skip that. Now, let me come back to the analysis of the model, okay? So once you have a model, you want to analyze it, no? So it's not enough to do nice simulations. So what are, as I told you, there are 3 parameters which are important. So for the moment, let me just mention that they are diffusing. So now you go down to 2 parameters: population density and active scent time. So now, so there is a parameter which is conveniently chosen from us to analyze the different state of the model, which is the spatial competition parameter, Z. And it is simply defined as the average space an animal occupies, if there was no other animal, divided by the average space available. No? So you have an animal, if you let it move, then of course eventually it goes all over. But if you divide by the actual average space available, which depends on the density, obviously, then you get an interesting ratio for spatial scales that gives you something meaningful. So more specifically, if you want this Z, is the number of distinct sites, because remember we are in a lattice, that a single animal visits in a time TA if there was no other animal around. There are statistical quantities you can measure, we know about, and divided by, the inverse of population density, the specific volume. Yeah? So that's the important parameter, and we call it competition parameter. So again, there is Sn over the inverse of the specific volume. So n is the number of steps within a time TA, because you can do continuous time simulation or discrete time. It doesn't matter, doesn't change much. So let's say it's continuous. So the number of steps in time TA. So and then again, as I was telling you, you can study this because this is a single animal. So you get an idea to make this ratio, and depending on the type of lattice you use, because we use Euclidean lattice, hexagonal lattice, and so on, there are different characteristics as a function of n. So you can study precisely what you have there. By the way, where is the clock? Oh, it's over there? That is co-working? Yeah, okay, thanks. So now, because I told you it's sufficiently simple, this model, now, and if you just, everything is diffusing, then it turns out that the entire type of different qualitative types of spatio-temporal dynamics only depend on Z. And I'm going to show you now some results based on that. Huh? So that's the main characteristics. So, okay, let me skip that one. Yeah? This is the type of density we looked at. So let's talk about the dynamics of the animal. Because I showed you about the descent, no? The dynamics of descent. So let's think about the dynamics of the animal. So you can just track one animal and see where it goes, no? So, and as I told you, from the data, we are looking at the mean square displacement. Why not looking at from the model, no? Obviously, so that makes sense, no? So let's look for the model. So now it's from the territorial random walk model. I'm plotting the mean square displacement of one animal, and the whole interaction with all the others. One animal, you tag one animal, and you look at that, and as a function of time divided by the active cent time. And that's the mean square displacement. So do you remember that we had the two examples where the things were saturating and things were not saturating? They were slowly increasing. The two different rats. I mean, the rats. And so that's, what am I changing here? Z. So that's a special competition. So you change the special competition parameter. Yeah. So if you make it very strong, remember Z is proportional to the active cent time, pretty much. So if active cent time is very long, nothing moves. So then you get frozen territories. So if they are frozen, then your mean square displacement saturates. But if actually things move, your box keeps moving because the cent, it's not, doesn't stay for long, like you saw, let's say the first little movie you saw about the cent, then things move, and then your MSD starts increasing forever. Now the saturation up there because it's periodic boundary condition, right? So that's just because of the sigma. Just consider up to here, no? Because that keeps going. So you have a sort of interesting effect here, which you see it's from here. You actually have some partial caging for some time, and then eventually it escapes, essentially. So how do you analyze this? So we wanted to understand a bit more. And so these partial caging effects, because you can say, I've modeled it, but what is happening really? Is there another way to characterize this different value of Z? Because this is a continuous, no? So to do that, you have to look at the different scales, okay? So before I tell you what we did, I'll show you a movie. This is a pretty cool movie, So my students did it like, whoa, okay. So we have an hexagon, so the structure is not, it's hexagonal lattice. I mean, there are some advantages of having the hexagonal lattice. Now, this animal has just left the cent here. There are different animals, different colors. And then what I'm going to do, I'm going to coarse grain as we look at it. So in space and time, really through a movie. So it becomes very clear. So you see, I'll come out, and then I'll slow down my sampling. So you will see that the frames at the beginning it did one steps, and then the frames, becomes, many steps. Yeah. So, okay, I'm zooming out spatially, so I'm coarse graining in space. One frame, one step. These are all the animals that are there. And then you see at some point, as I stop the spatial coarse graining, now the frame becomes many steps. Yeah. So I'm only showing you every certain number of steps. At some point, what becomes important is only the boundaries. All that matters is the boundaries. Yeah. And now if you think, okay, let me put the centroid of this boundary, and what you see, you have disks that sort of contract and, expand and so on. No? Fundamentally, that's what that is. I mean, for that type of regime, okay? Yeah? So this is a classical example. If you look at, once you look at it like that, then, it's a colloidal system. These are colloidal particles that actually have this peculiarity that, their size changes. But they are interacting, at the boundaries. Yeah. But there are tools in statistical physics to analyze colloidal system, this sort of, which are by taking snapshots. So you see, this is a single simulation. I'm not averaging over anything, but we can look at the spatial structure and try to notice, instead of looking at the animals over time, we are looking at the different sort of spatial and temporal scale, which are where the territories are, or if you want, where the centroid are, no? To understand what's going on for the different value of z that I was telling you about. So if you do that, before doing that, just to mention that the idea that I got, I was reading a paper from the 1920s, I think. So early observation of territorial biology. And when you read this paper from the 1920s, it's quite interesting. So they were looking at this territorial animal. So I don't think this animal flies, so I think it's just really like a mammal, okay, in some sense. So I just, it's too short, but I just want to read to you because you might not be able to read. So territories are thus partially compressible, but their compressibility is not complete, yeah? And so they are like elastic disks. This is exactly what we saw before, no? It's an elastic disk, what it says, of which there is a lower as well as a higher number which can be placed together to cover a given area. So somehow I was inspired by this, reading this, to just think about this coarse graining. So, okay, so now let's look at the centroid arrangement and see what you have as you change. You remember the parameter z I was telling you about? Yeah, this competition parameter. So as you increase, the value of z, you remember, so as z gets, as it was increased, when you get the high values, you just, saturate, and this one is the one that you keep, the MSD of the animals keep growing, no? So, and when you look at this, you can already see some big difference, no? Just by looking at that. So, this looks like a solid, no? Pretty much. This probably is like a gas or something, no? So when you study material, there are phase transitions to go from one state to the other. No? So in other words, what we decided to go after is that, so if for different z you have different structural characterization of the space where this animal move, so do we have phase transition, in the model at least. So we looked, and so you just analyze this single snapshot, simulation snapshot. So now you need lots of animals, you need big computers to do that. So there are certain quantity which represent when you have, different state, being solid, liquid, or gas, which is called the pair correlation function. And indeed, you can plot based on, you need lots of particles, 100,000 particles. So this is large number. Otherwise, you don't see anything. So these are always, they always start here, down here. I mean, I just displaced them just to see them, the difference. Now, this is the typical characteristic of an ideal gas. So that quantity, what it tells you is that the probability of finding another particle relative to an ideal gas. That's why it doesn't go to 0, it goes to 1. No? So an ideal gas, the particles go through each other. No? But actually, if you have a real gas, they cannot be at the same location at the same time. No? I mean, there is an exclusion. So that's a slight difference. But that's why it's 0. I mean, it's flat here, it's zero here, but then eventually it goes to some, because it becomes like an ideal gas at some distance. So I'm plotting versus the distance of the size of the particle. In our case, the size of the particle, the size of this territory, so the radius of this territory. So if you look at this case, this is a classical feature of a liquid. That's, you have this oscillation, and that, because you have, you think about one particle, around it, there is some impossibility to be the same location, but then there is a circle of particles around it, and then another impossibility nearly of being around it, and then, so that's why you have this oscillation, which decay. And then it's equally likely to find it anywhere, at some distance away. Now, when you look at this one, which is clearly like a solid, and the solid is, in the solid, you have hexagonal arrangement. So this is, I'm plotting radially. That's why you see this breaking of these peaks, because, you're plotting as a radius, so that doesn't fit with the hexagons, okay? So that's why. So in fact, when they study colloidal system, this is one of the features they look at radially to see if you have, created a solid or not, no? The surprise was, oh, what is this? There's no difference qualitatively, no? But you can see it's quite different, eh? Yeah, quite different. So, okay, so that was radially. If you want to do it, since I told you get an hexagon as a solid, if you want to do it in 2D, then you can clearly see. So that's your gas, that corresponds to that. This one is your liquid. As you see, you can see the ring around it. This looks like a solid. It's not. I'll tell you what it is. This is really a solid. So there was that one. Yeah. So if you want to do 2D, so okay, liquid, solid. Yeah. Now it turns out that I didn't know about Koster and Tholes. They got the Nobel Prize for topological studies on superconductivity. I think it's 2016. I think, and there was also a couple of other people. But they, long ago, they developed that theory of melting, solid melting, 2D solid. So, and how you melt a solid, you increase the temperature. So you increase, fluctuations. So, and what they showed, there are two ways to melt a crystal, a 2D crystal, not a 3D. So you either go through a first order phase transition, or, talking about what was the structure we didn't know what to call it, which looked like a solid by the top, or you go through another phase which is called exatic. And what you can see is that there is a special characteristic of this exatic, is that you have the number of neighbors in terms of the angles is 60 degrees pretty much, as in a solid. But the distance is not the same as here. It's not uniform, you see? That's why you have some sort of shift here, no? So if you plot the quantity relative to this, you are going to see the difference, yeah? And that's what we did. How many minutes do I have more? 10 minutes. 10 minutes, okay. So just to be more specific, so they talk about topological defects, and if you have a solid, you can have some defects, but you can see overall the structure is not changed, As you can see, these are the sort of pair dislocations. Okay, there are some details that you can ask me later. But if you have an exotic phase, you see the difference, no? So that's why I throw those lines just to show you that there is a difference in that arrangement. And so you can pick up and detect that. So, and that's what we did. So if you look at a quantity which is related to where the other particles are, remember, it's a centroid. And if it's a perfect solid, then their quantities sum up to 1, yeah? Because everything is 60 degrees. So, and then if you look at the cases, so this is the solid, and this is the exotic, and you see, as I told you, it's the same. You don't see any difference, but this is a gas, this is a liquid, it's very different, yeah? So, but on the other hand, if you look at the translation order parameter, now you see a difference between the solid and the exotic, which has to do with the distance where the other particles are. They're not all the same, And that's why you pick it up. And so then that's why we could show that it indeed was an exotic phase. So the way you identify the phase transition is indeed that you take those order parameter, liter psi, you have to do globally of the entire system, and you sum over, and this is your global order parameter. Let's get cut off there. And then you can see that as you plot versus Z, you remember we were looking at the changes as a function of the spatial competition parameter, no? So where it peaks, when you plot the variance and it peaks, that's when you have the phase transition. Now, our resolution of Z was not very big, but so it was not very fine. So then you have only 0.5, I think we looked at, but then you can see where you have the phase transition or when it peaks. So in other words, there is a phase transition for the exotic. No, this is the solid and this is the exotic, no? Okay. So then you can go and look at these topological defects, the presence of them and so on. And let me skip that because otherwise I won't have the time. Okay. So in other words, to recap, so you can look at the animal, you know, and see, and you look that you have complete frozen state when Z is very large, yeah, and the MSD of the animal so that you get trapped there, and pretty much you have a solid. Or, I mean, in these values, which are continuous, then if you actually look at the structure of the underlying spatial structure where they roam, then you can actually find these distinctions precisely, no? And so you can actually identify what this different curve belongs to there. Okay, so I'll tell you briefly. So when you have this big computer model, simulation model, these are large simulation models, then, well, I mean, of course, you can do analysis, no? But then you like to have some, I mean, you can't go with that model and make a study data, no? So it's not really convenient. So you need some approximation, no? And so then you have to develop an approximation. And again, how do you develop the approximation? Well, okay, the approximation is, you know, up to your creativity and how good they are eventually, you know, compared to the simulation, no? So now I just give you the idea how we went about to do that. So as you remember, all that matters was the boundary interaction, at least in the regime where not things move like crazy, no? So let's say the high dense liquid regime, and if you want also the solid, you know, the movement of those boundaries are very slow compared to the movement of the animal. So then you already think there is a timescale difference that you can exploit, no? To make models, approximate models. And this is what here I'm trying to picture here. So you have various animals on a line, that, you know, just to start always 1D with making this model. And then what these are scent marks, only the outer boundary, this one would be pushed back from that one, and this red would be pushed back for the presence of this one. There could be gaps there if you want, but yeah. I mean, this one is the simplified version in 1D of what's going on. Because you have these, the statistics of this is very different from the statistics of this. So now, to make it even simpler, you know, instead of having a line of individuals, you have two on a circle, okay? On a torus. So then it's completely simplified. And then you can study that. And then, so just to come back to what I showed you at the very beginning, you have the MSD, the mean square displacement, and instead of being, you know, saturating, it was slowly increasing. So this model gives you that. As you can see, I mean, trust me, it's square root of t that is increasing instead of being flat. Huh? You can see it slowly increasing, no? So you're already in a good position to say, okay, maybe that model is sufficiently good. And this is the occupation probability, okay, of the actual animal. So let me skip that. So we created this model, we tested it in 1D, then we went to the 2D, we tested, and it was sufficiently good to represent the simulation, and we look at the data. So I want to tell you just about the data. Let me just skip here. So these are foxes in Bristol over a very long period of time, I think 20 years or something, where the data are, so this is XY position, this you have the data. What you see around here is the fitting of the model. So I'm sort of, you know, representing to a little movie the way the fitting goes, no? And eventually you sort of well, I mean, you feed the parameter of the model, which, I'll tell you now what they are, but this is a sort of exercise you have to go through, and eventually you have to interpret, So, okay. I have a little table here to tell you. So what happened in Bristol around the 90s, there was an episodic of mange, which is like a scabies disease. Like 90% of the fox died. So then it's a perfect natural experiment for this sort of model, no? Or you have high density, boom, low density. And so you can go in and use them. You assume the model is valid both in this case and that case, and you look at the parameters, which are the average size of the territory, the way they move, and so on. And so that's where you're able to extract it. So perfect natural experiment. In fact, what I want to point out here is that the average animal velocity, so this is, okay, we modify a little bit the model. It was not just diffusion, you have correlation in a way. So then it goes up, yeah? So pre-mange, post-mange. So the animal has to cover a bigger territory, so they better do it fast if they want to scent, Okay, the population density, got reduced by a factor of 5. The active scent time, so that was an interesting one. So you can very precisely extract the active scent time, which normal condition was 5 days. So it became 3.5 days. No, and notice the error bars here. It's quite precise because you have this large data set. So to interpret, you can think that, of course, there are chemicals that determine the active scent, but there is also the decision of the animal to say, when do I actually move or not? No? So probably, they have other cues, acoustic cues and so on. If they hear nothing from the neighboring garden, then they sort of eventually realize, okay, nobody is there, no? And so therefore, what's happening? Oh. Okay, so, and therefore, that's why we believe that's the reason why the active scent went down, okay? So, and I think, let me conclude. Okay, so what I just show you, okay, that from microscopic animal movement and cell-mediated interaction, you have the emergence. As I told you about, there is a different philosophy of looking at this territorial, okay, that one is still available. I'm going to, it's okay, don't worry. So I'm going to tell you, so it's fine. So then you have from the micro to macro, emergence, there it is, of the distribution of animals. And I showed you that there was a sort of liquid, exotic, solid phase transition in the case of the animals, yeah. And well, okay, I skipped through, the results of the analytic model, and then I show you a little bit something about the fit to the experimental data, and I think I'm done. Thank you for listening.